All right. Good morning, everyone. This, I think, is where we left off last week in the presentation. I wanted to do this piece of algebra, this little introduction to special relativity, because it'll show us something. The algebra will show us something quite surprising, quite profound in a sense, as opposed to the buoyancy stuff that we're looking at. That the algebra was revealing just stuff that we already knew. This will be quite different. This is just a little introduction to the famous Michelson-Morley experiment, which is traditionally how you start introducing the concepts of special relativity. I say that for people who know, who've taken courses in special relativity. This is not actually where it begins. It begins with Einstein's paper of 1905, which he did not start with this, but pedagogically, this is generally the easiest way to introduce the basic concepts of special relativity before we get into the more sophisticated, beautiful, symmetrical questions that Einstein brought up to actually where he developed his theory. So we have the situation that it was well known in the 19th century that light is a wave. As a matter of fact, it was further known that light was an electromagnetic wave after the work of Maxwell in the 1860s, 1870s. Well, that raised an embarrassing question, because how do we see the sunshine? Yeah, if light is a wave and the astronomers tell us that space is a vacuum, how does light get from the sun to us? A wave needs something to wave, right? A wave needs a medium. You have no water waves without water. You have no sound waves without air. So how does the light get from the sun to us across this vacuum? Well, a vacuum was invented. It was called the ether, the luminous ether, and it just pervaded all of the universe. It was fixed, and everything was moving through this ether. It was known by then that the sun was moving, stars were moving. That was well known in the 1700s, that the stars that we see actually move literally in the sky, though very, very slowly. So it was understood that the sun is moving, and of course the earth is moving around the sun. So the earth has basic motion through this ether. The ether is fixed. And so if you were lucky enough to point a light beam directly in the direction that the earth was moving, it would look something like this, right? There would be the light beam going out at the speed of light, c. However, the earth, if it's moving in this direction, if we were lucky enough to pick the direction in which we directed the light beam in the same direction the earth was moving, then since the earth is following the light beam, it's trying to catch up to the light beam, it's following it, the speed that we would measure the light would not be c. That's its speed through the ether. That's its speed through the fixed medium. The speed that we would measure would be c minus v, because we're following the wave up. And if we had put a mirror here at some point in our apparatus, and we sent that very same light beam back at us, directly at us, we would be moving towards this back coming light. Then the speed would be c plus v. And this would be a very interesting experiment to do, because if we could go ahead and measure these things, we could actually find what is the true speed of the earth through the universe, right? Through the fixed medium of the ether. So it was something that was very intriguing for people to do. And the team that set up the apparatus in great detail, did it more than once over a number of years, is the famous duo of Michelson and Morley. And this is their apparatus. Here again, we have the earth, say, moving in this direction. And if we were lucky enough to pick and to situate this apparatus so that we have a light source here, we split it by a beam splitter. Some of it we allow to go straight through to this mirror, other we allow to move up at a 90-degree angle, both reaching two mirrors, and they'll come back to the joint place and then move on. And we will have this detection device, very similar, actually exactly as similar as the LIGO detection that we talked about last week, these interference fringes. We, of course, have no time to talk about this at all. We just want to say that when the two light beams come back, these fringes will tell us just, did they come back at the same time, or did they come back at different times? And if they came back at different times, by how much? Tremendously sensitive device to differentiate very, very tiny differences in the arrival times of these two beams in their trip, one going here and back and down, and the other going up here to this mirror and down. This device here can tell us whether they came back exactly simultaneously or in the most minute difference in time. So if we were lucky enough to send out this beam in the direction that the Earth was moving, of course, we don't know exactly what direction the Earth is moving. So what we do is we do this experiment over and over again. We do it, let's say, once a week, as the Earth is going around the sun, as the Earth is changing its direction going around the sun. We'll try every single direction possible. We'll do this experiment again and again. And at some point, we will have picked the direction where this will be true, that the light going to this mirror here would be in the same direction that the Earth was moving. Well, okay, so the idea is that when the light is going out, the Earth is moving in that direction. We're catching up to the wave in that sense. We're following behind it, and what we should measure, the speed that we should measure going out in that direction would not be the velocity of light c. That's the velocity it's going through the fixed ether. We would have to subtract our speed of the moving Earth of v. So it would have that speed going out to the mirror, okay? And we can use some algebra to calculate that. The time is equal to the distance over the speed. I'm sorry, yeah, the distance over the speed. The distance is L, the length from the central mirror out to the far mirror, over the speed, c minus v. So that will be the time out to that mirror. And the time back, now the two objects are moving towards each other. The wave is coming back towards us. We're continuing to move at the speed v. So we should measure the speed of the light as c plus v. And therefore, the time back would be the distance over that speed would be L over c plus v. We, of course, can't measure either one of these. This device, as sensitive as it is, cannot measure either one of these. It can measure the total time. It'll actually compare the total time out and back to the total time up and down. So the total time here is the sum of the two. Right? We want to add both the time out plus the time back. We'll call that capital T sub O. And we have a couple of fractions to add. We can certainly take the common denominator, very pretty common denominator, c squared minus v squared. I just multiplied those two denominators together. We used our sing-song algorithm of adding fractions. Okay, and c minus v goes into c squared minus v squared, c plus v times, et cetera, we multiply by the L's up on top, and we get that numerator. We multiply the L's through, the math gods are with us, the LV and the minus LV cancel out, and we wind up with a numerator of 2LC over the c squared minus v squared. So that would be the time, theoretically, if all this physics is correct, that would be the time out to the mirror and back. 2LC over c squared minus v squared. Allow me to do one thing. Traditionally, that c squared and the bracket is factored out. Notice that's the correct factoring, because you can check it by just multiplying c squared back through, and you will get c squared minus v squared. So that is the quite correct factoring, and c over c squared leaves me with a c down the bottom. And this is the traditional way in which that quantity is written. A numerator of 2L and a denominator of c times. It's very interesting, and if you know anything, if you've read any special relativity, you very much recognize this quantity, 1 minus v squared over c squared. So that's the time out. The time out and back. Now let's look at the time up and down that I'm calling. That is, if we have the motion in this mirror going in the direction of the Earth, this would be a motion perpendicular. Would not be affected by the speed of the Earth. it would, as the Earth was moving, the light would go up to the moving mirror and bounce back down again. Okay, and these two distances are the same. These two times would be the same. This is a completely symmetric motion, very different from the first motion where the speeds are changing. Here, the speeds are not changing. The speed is moving through the ether simply at c at the speed c. So how do we find the time of up and down? Well, the first thing to notice is that they are the same. So we just need to find one and double it. Of course, we're going to use the Pythagorean theorem, because as the light is moving from the mirror up to the far mirror, the Earth is moving. And so in this time tu, the light will move a distance c to u, and the Earth will move a distance v to u. This distance is L. This is our perpendicular distance to the far mirror, exactly the same L as the out and back, of course. So we write down the Pythagorean theorem in terms of distance, the hypotenuse and the two legs. We want to solve for t sub u, so we isolate it on one side, square everything out, do some factoring, and we can go ahead and solve for tu. Again, I'll do the same trick. If you allow me to, I will factor out that c squared. Now I'm factoring out of a radical. The Pythagorean theorem has given us a radical here in this expression. I want to factor out the c squared as a radical. It'll come out as a c. Again, you can check that by multiplying the c back through. The first thing you have to do when you bring the c under the radical is you got to square it. And that will indeed give us back c squared minus v squared. And these two times are the same, so all I need to do is double them. So the time which I'm calling up and down, up in terms of this picture, the time up and down, that perpendicular distance to the motion of the Earth is simply, I'm calling a capital T sub u, and that's just the double of either one. So again, we have 2L over C times the radical. Notice the two expressions, T up and down, which we just derived, and T out and back. They're very, very similar. Okay? Matter of fact, the numerators are the same. They both have the speed of light down the denominator. The only difference is in the time up and down, we have the radical of this expression, 1 minus v squared over c squared. And in the time out and back, we have the full expression, simply 1 minus v squared over c squared in the denominator. These two numbers are not the same. These two times are not the same. That very sensitive device will detect, if the physics is correct, we will detect a difference in their arrival times. The interference pattern that we will see will show that these two lights have not come back at the same time. The pattern will shift, and it'll shift. The device is so sensitive that it'll actually tell us how much time there was by a shift, if there was such. Well, which time is bigger than the other? Well, the only difference between these two times is one has a radical in the denominator and one has the full term in the denominator. But guys, this term is less than 1, right? V squared over c squared is a fraction. V squared is less than c squared. And so we're subtracting a number from 1. This expression, this very famous expression, 1 minus v squared over c squared, is less than 1. What happens when you take the square root of a number less than 1? You get a bigger number. Yeah, the square root of 9 is 3, but the square root of a quarter is a half. When you take the square root of a number less than 1, you get a bigger number. The square root of a quarter is a half. So in fact, this number here, this, which is in the denominator, is bigger than this number here. This expression here has a larger denominator. This is a smaller fraction. The time up and down is shorter than the time out and back. Okay. Tu has a larger denominator than T sub O, and therefore these times are not the same. In fact, the time up and down is shorter than the time out and back. However, when this experiment was done over multiple years, where the devices that they were using, the apparatuses they were using, was becoming more and more sensitive. Michelson, of course, is a very famous American physicist. He's the first physicist to win the Nobel Prize, the first American physicist to win a Nobel Prize. He won it by measuring the speed of light. He was an expert in measuring the speed of light. That was his, that he devoted his entire life to the study of the speed of light and all the other phenomena around it. So we can trust his results. And his results were that he never found the time difference. That interference pattern always showed that the light came back at exactly the same time. Although the algebra clearly shows, assuming our physics is correct, assuming that we do have this ether, that the light moves through the ether at a constant speed, that these times, in fact, are different. One has a radical term in the denominator, and one has exactly the same term without the radical. What to do? What to do about this conundrum? That the math is telling us one thing, and the experiment, the actual nature, the world, is telling us something else. Well, if you look at the apparatus, and you say, well, the problem here is that this time here should be exactly the same back and forth as this time here, but it's longer for some reason. I'm sorry, the math tells me it should be longer, but it's not. It's the same time. But the math tells me that this trip should be longer. Why isn't it longer? Well, one thing you could do is you could shorten the trip. You could simply say that the distance from here out to the mirror is not L. It's something shorter. And that's what's, and that shorter distance is exactly compensating for the time. So it will come back in exactly the same time, which is what the experiment is showing. That we can't argue with. So this is a crazy idea, perhaps, but maybe the idea that since the Earth is moving in this direction, that somehow or other the ether is pushing up against them. I don't know, but one possible solution would be that this distance is actually not as long as this distance, that somehow or other this distance contracts because of the motion of the Earth through the ether, and it contracts just for the right amount that the two times will be the same, which is what this interference pattern shows. So let's take a look at our two times again. Here's the time up and down. Here's the time out and back. We need to shorten this distance out and back. This is the only way that we're going to make, we certainly can't change the two. We can't change C. We can't change the speed of light. The only thing that we could possibly change is L in this equation. So let's call it K for contraction. And let's say that the time out and back is not the full L, but it's some contracted distance K. What must K be to make this equation true? Okay, I've got one fraction over another. We've got some cancellations here. The twos cancel, the C's down the bottom cancel. I simply can cross multiply what's left to bring this expression here up. Solving for K, I have L times the expression over its radical, right? 2 over radical 2 is radical 2. So K would be, according to this algebra, would be L survives times the radical, that famous radical. Notice that is shorter than L. Okay, L times this radical is short because 1 minus v squared over c squared is a number less than 1, and we'll multiply, and its radical is less than 1. And so we are multiplying L by a number less than 1. We truly have a contraction here. If the apparatus in the direction of the motion of the Earth contracted by just that amount, the Michelson-Morley experiment would be explained. Nobody particularly liked this idea, but two very well-known physicists, particularly the man down the bottom, Heinrich Lorentz. He is the godfather of 19th century physics as we move into the 20th century. He is the great mentor of Einstein. He is by far one of the most, probably the most famous physicists of his time. Even he did the algebra just to take a look at what it would mean, and he tried to come up with a theory as to what the electrons would be doing or something or other, something to be compressed to make this happen. And again, you can show in the algebra that this, in fact, that new K will, in fact, make the times the same. Well, this is not the reason. It's not that the ether is pushing against the mirror or anything like that. We know that this is the famous length contraction of special relativity. There's also a time contraction in special relativity, and they all have this incredible expression the square root of 1 minus v squared over c squared. So that's really all you have to do, is you just have to contract this distance, L, by the factor square root of 1 minus v squared over c squared, and then the times, in fact, will be the same. Why is this? This comes out of Einstein's theory of special relativity. He has a totally different take on this, different postulates. One of them being that the speed of light is measured the same no matter how fast you're going and no matter what direction. Yeah. So this whole Michelson-Morley experiment is a complete ruse. You would never come up with any change in speed, because one of his postulates of special relativity is we always measure the speed of light to be c no matter what. Okay, as long as you're moving at a constant speed. Okay, but I asked you to look at the algebra one last time as we leave this. Take a look at this expression, L times 1 minus v squared over c squared. Certainly we're assuming that v is less than c, and we have a number less than 1 multiplying by L. Look what happens if v is equal to c. And let's stress this equation. Let's look at its extremes. If you made v equal to c, if the Earth was moving at the speed of light, then this term becomes 1. V squared over c squared becomes 1. We have 1 minus 1, which is 0, and we have L times 0, which is 0. This would have no length at all. There would be no length from the beam splitter to the outside mirror if the Earth was simply moving at the speed of light. Sounds a little crazy. Okay, gets worse. Suppose that the Earth was moving at a speed faster than the speed of light. Now we have a number larger than 1. Now we have a negative number under the radical. We have 1 minus a number larger than 1, which leaves me with a negative number under the radical, which gives me an imaginary number. That's even crazier. The distance between the splitter and the mirror is now an imaginary number. This is what the algebra tells us, if in fact you could move the Earth at those kinds of speeds. The algebra is telling us in a very naive way, you can't. The Earth, in fact, nothing made of mass can move at the speed of light, never mind moving faster than the speed of light. Of course, it's Einstein's theory, which will show why this is the case. But it's here we see the beginnings of it, just in the simple algebra, just in the simple analysis. And again, when we did this analysis, we worked with these equations, we weren't thinking about constraining the speed of the Earth. Okay, that was not on our mind. But here, if we try to stretch this thing, we will come up with conclusions which we really don't want to come up with. So we want to back off and say, no, it's not possible to be moving at or faster than the speed of light. And in fact, the special relativity shows that to be the case. So here we have a conclusion from algebra that is, in fact, quite profound. Okay, very quickly, just in 5 minutes, I want to just take a look at this fun thing of balancing chemical equations. If you remember from your high school chemistry, what's behind all this is the conservation of mass. You have to have the same number of atoms on one side of the reaction as you do on the other. You can't lose track of the masses of these atoms. So the simplest one would be where all the masses are preserved in a very simple way, creating table salt, sodium plus chlorine. You have 1 sodium and 1 chlorine on one side. Yeah, you got 1 sodium and 1 chlorine on the other side. Not much to do. However, if you want to take the reaction of creating water from the hydrolysis of hydrogen and oxygen, now you have a bit of a problem, because here the oxygen is not balanced, right? You've got 2 oxygens on the beginning side and only 1 on the other. Well, we could try to put 2 in front and give us that 2 oxygens. Okay, then the oxygens are happy, but now the hydrogens are not happy. Okay, we've got only 2 hydrogens on one side. We've got 4 hydrogens on the other. Well, not too hard. We just simply put a 2 in front of the hydrogen. And if you take a look at that, that is a balanced equation, right? You've got 4 hydrogens on each side. You've got 2 oxygens on each side, and we're good. This, of course, is very simple. We can do this by eye, but you can imagine if the reactions get more complicated, we may want to try something, more mathematical. So let's look with this very simple example. Let's go through it again using the algebraic technique, and then I'll just do one more. So let's put just numbers in front of our compounds, X, Y, and Z. We have three unknowns, X, Y, and Z, and we'll generate two equations because there are two elements, hydrogen and oxygen, okay? Of course, we need to have X, Y, and Z be integers, right? We need whole numbers of atoms. So in our solution, we're looking only for integer solutions. That'll be a constraint as we finalize the numbers that we pick. The hydrogen equation, if you have X in front of that, you'll have 2X hydrogens on the left-hand side. Okay, you'll have two hydrogens for every X. So you'll have 2X on one side, and sure enough, you'll have 2Z on the other side. The oxygen equation, again, we'll have two Y's on the left-hand side. However, whatever Y is, we've got two O2s for each of those. We've got two Y, and we only have one Z of an oxygen on the other. So there are our two equations, okay? Not too bad. Right away, we see that X is equal to Z. And here, in the other one, we see that Y is equal to Z over 2. So we have X and Y both in terms of Z. We just need to pick a reasonable Z and we'll be done. Since we need all of our numbers to be integers, we want to pick Z to be 2, so Y will become 1. If you made Z 1, then Y is a half. Well, that's a no-no. So you want to pick the simplest values to get whole numbers for everybody. And the only constraint here is that Y is equal to half of Z. So make Z 2. We make Z 2, Y is happy as 1, X is the same as Z. So X is also equal to 2. And there's our balanced equation. Okay. All right. Let's go to a more interesting one. Let me move down here to this guy here. Okay. Actually, I actually want to go. Yeah, this is a good one. Okay. So here we have iron chloride, sodium hydroxide, which is lye, creating iron oxide, and again, salt. We have 5 equations. Why? Because we have 5 equations and 4 unknowns because we have 5 elements. Each element will create an equation, okay? And each compound will create an unknown. We're putting a number, X, Y, Z, W. We're putting an unknown number in front of each of these compounds. So we have 4 unknowns, but we have 5 equations because we have 5 different elements. And we just generate these, okay? We'll look at the iron. We've got an X times 1 on this side. We go over here and we have just 1 iron in front of Z over here. Chlorine's a bit more interesting. We have 3 chlorines for every X. So we have 3X chlorines on one side, and we just have the 1 chlorine for the salt for W on this side. For sodium, we've got just 1 Y and 1 W. For oxygen, we just have 1 Y, but we've got 3 oxygens for every Z over there. And finally, the hydrogen equation, we have just 1 Y on this side, but 3 Z hydrogens on the other. So we've generated an equation for every single element. 5 elements, 5 equations. But there are only 4 unknowns because there are only 4 compounds. This could be a problem algebraically. We've got really more equations than unknowns. Okay, we could have an inconsistency here, but nature is saying, no, you won't. This actually is a solution that happens in the real world. Okay, this should work out. This happens in the lab. So you will not get an inconsistency, although mathematically it's possible. So I just mentioned that in red as a mathematical possibility, but not to worry. So this is an art form in a sense of trying to look for these. The more you do these, the more you get used to it. My strategy here is I'm going to try to write everything in terms of X's. Once I've got everything in terms of X's, I pick a nice X and everybody else will fall out and I'll have a balanced equation. Notice my first equation is for free. Z is equal to X. Now I look at W is equal to 3X, so I'm good there. And now look at that, Y is equal to W and Y is equal to, what am I saying? Y is equal to W. Yeah, Y is equal to W, but we already agreed that W is equal to 3X. So Y is also equal to 3X, okay? And finally, we have y is equal to 3z, but we know z is the same as x. So if I make x equal to 1, everybody will be happy. Okay, z is the same, w is 3 times x, y is the same as w, so it's also 3. I put all those numbers in front of the compounds, and if you look at this, you do have a balanced equation. Okay, and look at your ions. You got 1 ion on one side, 1 ion on the other. You've got 3 chlorines on one side, and you've got 3 chlorines on the other. You've got 3 sodiums on one side and 3 sodiums on the other. 3 oxygens on one side, and there it is, 3 oxygens on the other. And finally, 3 hydrogens on one side and the 3 hydrogens on the other. So if you're interested and you want to play with these, if you're in a member of your high school chemistry, I've got plenty of examples here to look at with these equations. This is actually a very interesting one. This is a nice substitution. If you want to look at this, the burning of benzene is actually a bit more non-trivial in terms of finding the nice substitutions that'll work. And I've got some blowing up ones, nitroglycerin and TNT, and we've gotten some fun here. And guys, and I got a bunch for you to try. Okay, all right, and the solutions are in the back of the presentation. All righty. So just to show some applications of our algebra in the real world. Let us now start our next presentation. We're really now ready, guys, to go into our deeper waters. Before I start, are there any questions so far, particularly on the algebra or whatever of the Michelson-Morley experiment? I know I went through that quickly. There's a lot of physics there. But hopefully focusing on the algebra, algebra was pretty straightforward. Any questions? Okay, I'll take that as a no. All right. I have one last pretty piece of algebra for you, just a pure piece of algebra. We want to derive the quadratic equation. Okay, we want to derive the quadratic formula. And it's a very pretty piece of algebra. It's done by what's called completing the square. Let's start with one that we know. We have a quadratic equation, x squared minus 6x plus 5, easily factored into minus 5 and minus 1, finding the solutions of 5 and 1. Let me show you how you would do that using completing the square.
One question, Peter.
Yes, question.
Yeah. I don't know if Sharon wants to ask it herself. I'll just read it. Why do you call a radical what I call a square root?
Same word. I apologize for using my word. It is the same word. Yes. You can talk about the square root of 3 or radical 3. Okay, let's take a look at this equation again. But I want to now, instead of factoring it, I want to use this method, this algorithm of completing the square. So here are the steps. I'll bring the 5 to the other side, and now I'm focused on x squared minus 6x. What I want to do is I want to take that x squared minus 6x and I want to write it as a perfect square. X minus a squared, where I want to pick the right a. Well, we know from the algorithm how you multiply these terms together that if I want to do that, I need to look at that minus 6. I'm going to cut the minus 6 in half. X minus 3 will give me the minus 6 term. So I look at that middle term of minus 6, cut it in half, and there, if I say x minus 3 squared, I'll get the x squared and the minus 6x. Okay, I'll get more, true, but I will get the two terms that I am looking at, x squared and minus 6x. That's the trick to completing the square. That's why it's called that. Okay. You pick a term here, minus 3, so that when you square it, you get the middle term that you know you must have of the minus 6x. Now, of course, when you multiply out x minus 3 squared, you're also going to get the back term, which is 9. Minus 3 times minus 3 is 9. If you want to preserve this equality and you're adding a plus 9, you better add a minus 9, which we do. We add a minus 3 squared. And that continues to equal 5. I'm sorry, equals minus 5. We have preserved our equality, okay? By compensating, when we did the x minus 3 squared, we compensated for this extra plus 9 term by adding a minus 9 term. Well, now I can just continue the algebra. I can bring the minus 9 over to get a 4, and I can take the square root of both sides, okay? I have the square root of 4, which is plus or minus 2. I do want to use a plus or minus 2 because I'm solving for a quadratic equation. I know I'm looking for 2 different solutions. So I'll write that radical 4 as a plus or minus 2. And I'll simply bring the minus 3 over. So I'll get plus 3 plus 2 and a plus 3 minus 2, which will generate my 5 and my 1. You'll say, well, why did you go through all this craziness when the factoring gave us that? True. What happens when you can't factor? Okay. All I need to do is to come up the works is to change that plus 5 to a minus 5. You can't factor that, guys. Okay. You're not going to get the factors of minus 5 to get you minus 6, right? To get the minus 5, you need both a plus and a minus. You ain't going to get the 6 that way. This will not factor. So let's try completing the square, okay? We'll start the same way. We'll bring the minus 5 over to the other side. We'll take a look at that minus 6 middle term, minus 6x. I know I want to go ahead and add, use the minus 3, half of that minus 6. So now I've completed the square by having x minus 3 squared will give me, what I have, x squared and the minus 6x. It'll give me a little bit more, but I'll go ahead and compensate that with the minus 9. And now I've got, instead of a minus 5 over there, I've got a 5 over there. Well, now when I bring the minus 9 over to a plus 9, I've got 14. That's not a perfect square. So when I take the square root of both sides, I'll get plus or minus the square root of 14, but I'll finish off the same way. I'll bring the minus 3 over, and I will have 2 solutions. I will have x is equal to 3 plus a radical 14, and 3 is equal to minus radical 14. And they are the solutions to that equation. Just for fun, let's go ahead and take that first solution and show that it is in fact a solution. Let's do a check. I want to do this just to show how powerful our little algorithm is of multiplying 2 terms in a bracket. Okay, let's multiply 3 plus radical 14 squared. Okay, it's just like x plus 3 squared. It's the same algorithm. Okay, and then of course we have the minus 6 times the radical. That's not a problem. We'll just distribute the minus 6 through. Now I want to just show that this, using our algorithm of 3 plus radical 14, okay, so-called, sometimes called the FOIL method. I don't like that, but that's what it's called. But we'll go ahead and use our algorithm. We know we're going to multiply the front terms, 3 times 3. We'll know we'll multiply the back terms, radical 14 times radical 14. And we have the middle term. We have a middle term of 3 radical 14 twice. So we have 2 times 3 radical 14. That's exactly the same algorithm we've been using forever here. If we wanted to multiply x minus 3 squared, for example. Well, we need to clear this up. 3 squared, of course, is 9. And I'm sorry, we need to multiply the minus 6 through. So 3 squared is 9, and radical 14 times radical 14 is 14. That's very pretty. And look at our middle term, why we use that square. We use that square because the middle term will drop out. That's the whole deviousness here of using this kind of algebra. The middle term, that nasty middle term, goes away, and all we're left with is whole numbers, which indeed add up to 5. This is, in fact, a solution. As strange as they look, we're not particularly happy with numbers like this, but there they are. Those are the 2 solutions to our equation. So this algorithm, I'll leave it up here at top. This algorithm of completing the square, let us now do using pure algebra. This is a very nice piece of, I think this is the last piece of just pretty pure algebra that we will use, because from here we will start our study of analytic geometry. We'll be using our algebra intensely all the time, but this is just one last piece of pretty algebra. Okay, let us apply the algorithm up above, not with 1 and minus 6 and minus 5, but to A, B, and C, and see if we can handle this working purely algebraically, following the algorithm of completing the square. Well, the first thing we have to do is have to get rid of that A, right? Because the whole thing depends upon having just an x squared in front. So we got to get rid of that A. So we have to divide the whole equation through by A. That's the whole equation through by A, guys, right? Every single term gets divided by A, even the 0. And 0 over A is no trouble. It stays at 0. Okay, now we can go ahead and do the next step, which is to bring that number term, C over A, over to the other side. Okay, it becomes minus C over A. And now I stare at x squared plus bx over A. I want to write that as a perfect square. I know the way to do that is to take the coefficient in front of the x, b over A, and cut it in half. B over, I'm staring at that b over A, and the way to make it into a perfect square is to cut it in half, make it into b over 2A, right? To cut it in half. Now, if I square that term, x plus b over 2A, I will get my x squared. I will get a middle term of BA over BA times x. But of course, I will get that extra piece, right? I'll get b squared over 2A squared. So I better subtract it to keep the equality the same. I've done that just as I've done before, and that now continues to equal minus C over A. Okay. Let's go ahead and continue the algorithm. Let's bring that new term, that compensating term, over. Notice I've got a 2A there and a 2A there on the right side. One is squared. Let me go ahead and square that common denominator. I got a 4A squared. I got an A, common denominator of 4A squared. We do our sing-song algorithm of adding up common fractions. 4A squared into 4A squared goes 1. 1 times b squared is b squared. A into 4A squared is 4A. 4A times c is 4AC. Yeah, I think the old mental muscles are kicking in on some of you as long ago as it is. B squared minus 4A squared, 4AC. I've heard that before. Yes, you certainly have. Okay. So here we are. Yes, question?
We can't hear you.
Oh, am I breaking up?
Yeah.
All
Yeah,
right,
you froze for a little bit.
All right, let me go ahead and close
Would
my
you-
video. Oh,
Would
man.
you go back a couple of steps?
Yes, I will.
Where you started the red stuff is where you started breaking up.
Okay, when I started the algebraic steps?
No, the red, where you got down
The
to
red,
the B over
here,
A in
down
red,
here?
that's where you started
Okay,
breaking up.
great. Okay, so here we are here up above. Applying our algorithm, we want to bring that plus CA over to the other side. And now I want to complete the square. I'm looking at this thing here, and I want to write this as a perfect square. I know the way to do that is to look at that middle term and cut it in half. So by taking this b over 2a, cutting that in half, that's b over 2a. Cutting b over a in half will give me b over 2a. So that's the way to complete the square. The way to complete the square is to say x plus b over 2a squared. That will give me x squared and b over a times x. And of course, it'll give me a little bit more. It'll give me the square of the back term, b over 2a squared. So I need to compensate by subtracting the b over 2a squared. I preserve my equality. Therefore, that longer term continues to equal minus c over a. Okay. So let me do a little bit more algebra. I'll throw this term here, this compensation term, over to the other side. I notice that I can go ahead and simplify this by getting it all under one fraction. Let me square out that term. It got denominators of 4a squared and a. Not too hard to get a common denominator of 4a squared. When you use that common denominator of 4a squared, son of a gun, if you don't get a term which certainly should sound familiar to some of us, b squared minus 4ac. Okay, we've heard that so many times in our work with the quadratic formula. So here we see the quadratic formula begin to develop in front of our eyes. All right, so here we are. kind of taking the first term and the last term, putting them together, leaving all that stuff out. Here we are. We want to finish off. Okay, we want to take the square root of both sides. I'm trying to solve for x. So we'll take the square root of both sides. Okay, and I'll simply get this, and I'll get the plus or minus this long term. Okay? This whole thing is under the radical sign, everything, and the whole fraction, numerator and denominator, plus or minus. Okay, but notice that 4a squared is a perfect square. Okay, so the square root of 4a squared is in fact 2a. And now we're pretty much done. Yeah, the square root of b squared minus 4ac over 2a. Yeah, we're getting very close. All we need to do now is bring the b over 2a to the other side. And solving for x, I get minus b over 2a plus or minus that radical over 2a. Common denominator is right there of 2a, and ta-da, we have the quadratic formula. Okay, minus b plus or minus the square root of b squared minus 4ac over 2a. Okay, we've simply taken the completing the square algorithm and did it once and for all, and we no longer need to do the complete the square. We can just simply notice what a, b, and c are and substitute them in. Let's take our very same problem. Let's take this very same problem here, and let's apply the quadratic formula. We notice that a is 1, b is minus 6, and c is minus 5. Let's just plug it in. We have a minus 6. We have 36. We have 4 times a times minus c is 20 over 2 times 1. Okay, we'll do some arithmetic here. 36 plus 20 is 56. The square root of 56. 56 is 4 times 14. So I can take the 4 out as a 2 and leave the square root of 14 inside. And of course, 2 over the 6 will give me 3. And now 2 over this 2 will cancel out. And I'm left, sure enough, the arithmetic will give me 3 plus or minus the square root of 14, right? Just what we had. Okay. So the quadratic formula is simply using the completing the square once and for all, once we've done it in pure algebra. And we will find the quadratic formula useful, right? Because we will come across quadratic expressions that nature will present to us that we can't factor. So we will fall upon this. And you must admit, it is a very pretty piece of algebra. Using the algorithm of completing the square in pure letters gives us this very well-known result. Okay, proof that even I can make algebra mistakes. That review test, problem number 22, asked to find a factor of this expression. And I said, oh, go ahead and find both factors. So we factor out the 4x squared, and we're left with this thing here, which was the answer. The answer they were looking for was this other factor. I went ahead and I factored it. That's not right. Okay. +1 times -1 is not a +1. Okay. This, in fact, does not factor. And that was pointed out to me by an email by Bob Taylor. Thank you, Bob. Peter, they do not factor. Something is wrong here. So yes, you have to use the, if you want to continue, if you had this as something to solve, you would have to use the quadratic equation. Okay. We could do that. A is 3, B is -5, and C is 1. We could stick the whole thing in, do some arithmetic, and you'll wind up with the correct, but not particularly a happy number of 5 plus or minus radical 3 all over 6. That's a far cry from ±1, but those are in fact the factors would be the solution. Besides x is equal to 0, 4x squared is equal to 0 makes x 0. These would be the other two factors if you wanted to set this equation equal to 0. All right. Functions. We go into deeper waters here. I start with the problem. The length of a rectangle is twice the width. The perimeter is 30. Find the length and the width. Okay. This we know how to do. Okay. We will let W be the width and L be the length. And we're told that L is equal to twice W, and the perimeter, 2W plus 2L, is 30. two equations and two unknowns, we use our substitution method. We'll take L to be 2W, put it into the perimeter formula, 2L plus 2 times L, 2W plus 2 times L, 2 more W's is 30. We get 6 W's equal to 30, W's equal to 5. L is twice that, which is 10. Okay, very good. What's my point? My point here is in looking at these equations that we developed, we see that L depends upon W, actually in two different ways. L can be computed from W. In the first way, L is equal to 2W. Okay? We want to introduce a new concept here and a bunch of new words, a bunch of new vocabulary, and a new notation for this. The idea that L depends upon W, that a variable depends upon another variable. We say that L is a function of W. We write it as L is equal to f of W, and f of W is in fact this 2 times function, okay, twice W. F is the name of the function, and this very interesting new notation, f of W. So f of 1 is 2, because whatever you put in for W, you get 2W. The function will give you twice that. So f of 2 is the same thing as 2 times 1. F of 10 is the same thing as 2 times 10, et cetera, et cetera. We've moved away now, guys, from symbolic arithmetic. Algebra with this, by introducing this concept of a function in algebra, we've moved away from symbolic arithmetic. F is not a number. This is the first algebraic expression we've written down where F is not a number. This bracket here around W is not a multiplication sign. It is a brand new piece of notation. It is the function notation. Okay? Functions are not only very important in mathematics, one could argue that they are among the most primitive and most fundamental concepts in all of mathematics, and certainly it is true in our work. We will be working, from now on almost exclusively with the idea of functions. Functions create tables of values, right? As we have different F's, different W's, we'll get, the function will generate for us different values for the function of WL. It'll simply, in this particular function, it'll simply generate all of its doubles. Even for any general W, any W you like, the function will generate 2W, as is the computational rule. The perimeter, right, also is a function of W. This was allowed us to do the substitution, right? We found that given the perimeter being 15, then the length is 15, is 30. I'm sorry, given that the perimeter is 30, the length is 15 minus W. If you look at this equation here and solve this equation for L, you will get 15 minus W. So we have yet another function of W. I write this function with a different letter, G. The traditional letters that mathematicians use for functions are F, G, H, and their capital letters. Those are the kind of the first go-to letters that you would use to designate functions, all else being equal. So I have a second function of L as W, and it generates its table of values. Okay, for each one of those W's, I simply subtract that W from 15, and I get a table of values. What this algebra that we've learned how to do, right? What this substitution method has done is simply sifts out for us and find us a way to find, the same set of values in both tables. That's ultimately what the algebra has allowed us to do. It's a very, very nice what the algebra. We don't need to hunt through the table of values in these functional relationships. The algebra shows us how to do this with the substitution method. That's essentially what's going on. We find this this pair of values, this width and length, that makes both functions true. And this table of values, guys, right, is a very tiny percentage of all the rectangles in which the length is twice the width. This is a very tiny subset. This is just a sampling of all of the different kinds of rectangles in which the perimeter is 30. Let me show you what I mean. In terms of these table of values, here is all of the rectangles in which the length is twice the width. There are an infinite number of them, okay? Here I'm going up to a width of 6. If you can see the 6 down here. There's lots and lots of rectangles, and any one of these pairs could be in our table of values. Oops, sorry. Mistake. Sorry. Okay, so I wanted to stop at a certain place. Okay. The other function, here are all the rectangles which have a perimeter of 30. There are an infinite number of these rectangles which have a perimeter of 30. The table of values that we generate is only a tiny sampling of those functional values. Many. But now what the algebra allows us to do is to sift through and find just a pair where the width is 5. You can see this 5. When the width is 5, the length is 10. Not only is the length twice the width, but in fact, the perimeter is 30. So my point here is that the function is deriving a relationship between the length and the width, and the number of pairs which have this relationship is in fact an infinite number of pairs. Okay, a couple of exercises for you guys to try with these new ideas. I didn't provide the answers to these. I'm sorry. I meant to add the extra thing, which I have the answers to. When I put this out on YouTube today, I'll throw you guys a quick email, which just has the solution slide to these questions if you want to take a look at them. All right, I'll stop here after this slide for some more questions. Here's a nice kind of visual view of one way to think about functions. You can think of it as a machine that has inputs and outputs. Okay, the inputs to the machine are these numbers. You pour them in. We call them the numbers x, and the outputs are the function of values. This new notation. F of x is how it's read. It's not f times x because f is not a number. Okay, it's an idea. It's a relationship in which we can compute a number from x, and the function machine itself, is called f. So a function is a computational rule which operates on each input number and produces a single associated output number. That's very important. The rule has to be very unambiguous. You give me an x, I'll be able to compute for you a single f of x for that particular x. When x is the input value, then f of x is called the function of value of x. And so here we have another function, 3x minus 1, and these would be the function of values. The function of value of 1 is 2, the function of value of 2 is 5. The function of value of any number z is 3z minus 1. Okay. A bit more vocabulary here. Certainly, functions, as you look at the computational rule, they can restrict. Some numbers will not serve as inputs. Okay, you'll get some mathematical no-nos. If your function, for example, is 1 over x minus 1, you really can't compute f of 1. F of 1 will give you 0 in the denominator. You can never put 0 in the denominator, right, in algebra. So 1 is not a valid input to this particular function, 1 over x minus 1. Any other input would be fine, but not 1. Here's another function, the square root of x minus 1. Notice that g of any number less than 1 would give us a negative number under the radical sign, right? If you put in, for example, a half, you get negative a half. Okay? Well, that will give us an imaginary number. Imaginary numbers are fine, but they're not fine for us. We're not working with imaginary numbers, okay, in our course. So we would restrict that function to all numbers greater than or equal to 1. And those numbers less than 1 would not be valid inputs for this function. And if we're working in applied mathematics, which we will be doing so often, take our rectangle function of the length is twice the width, then really any width less than or equal to 0 really makes no sense. You can't have a length that's 0 or less. So geometrically, we would restrict the function to only positive values of w. You, of course, could put in any value you like for w mathematically, but given the context of where this function came from, those numbers would not be valid inputs to this function coming out of the geometry of the problem. And just another piece of vocabulary, the set of valid input numbers that we do have for any function is called the domain of the function. And we'll be looking at different domains of functions. Some functions have restricted domains and others don't, particularly when we get to mathematical laws. Mathematical laws are valid for certain pieces of the domain, and they're not valid for other pieces of the domain. We saw that, for example, with that relationship of the time of special relativity. Turns out that you really can't put a velocity greater than c. If you do that, you'll get physically craziness. So that function really, we need to restrict what the value of v can be by its relationship to c. So an example of a restriction coming out of nature's laws. We stop here for a minute and open up the mic or look at the chat box. Any questions so far? First of all, has my sound become stable?
Yes, Peter.
Okay. Any questions about this idea so far? We've moved away from symbolic arithmetic. Guys, you see my point, that this f is not a number, that bracket around it is not a multiplication sign. We've introduced a new piece of notation, this functional notation. It's one that if you haven't seen it in a long, long time, we're going to have to get used to it again because I'll be using it constantly. Any questions? Anybody want to unmute themselves? All right. Formulas certainly give rise to functions in a very, very natural way. We'll take the area of a circle, pi r squared, and we would say that the area is a function of the radius. It depends upon the radius. How? Computationally, pi times r squared is the computational rule, very unambiguous rule. You give me a radius and I'll give you an area. Okay. Since, again, building up some more vocabulary, guys, since a depends upon r, we say r is the independent variable and a is the dependent variable. A depends upon r in our functional relationship coming from our area formula. Certainly, we can solve algebraically for r. No reason why we can't say that r is equal to the square root of a over pi. And therefore, you could say that the radius depends upon the area. You certainly could. Okay, but when you take a look at that computational rule, here you'll have to say it's the positive square root. Otherwise, you'd have an ambiguity. Okay, in solving quadratic equations, we often do plus or minus. It makes no sense to say plus or minus here. Radiuses are positive. Okay, this function relationship. Okay, we have a positive area. You're going to get a positive radius. Okay, so this, if you wanted to write the radius as a function of the area, you'd say it is the positive square root. Not a big deal, but you need to keep that fact that the computational rule is completely unambiguous. Okay, and again, here you wouldn't certainly want to put negative numbers under the radical sign, but that's no problem because we don't have negative areas anyway. So the geometry naturally filters out any of those invalid inputs. Sometimes a function can require more than one independent input. The perimeter formula is a nice example. You need the width and the length. So we could write the perimeter is a function of both w and l. Okay, you'd write that as h of w comma l is the notation that would be used. And the computational rule would be 2w plus 2l. For example, the rectangle that we were working with. So p of 5 comma 10, the area, the perimeter when the width is 5 and the length of 10, the computational rule gives 30. In general, we will not be working with functions of more than one variable. We'll be surprised how far we can get by working with functions of just one variable. One of the ways in which we'll avoid that is by having those two different relationships as we had in the word problem. We'll not only know that the perimeter is 30, but we'll also know something else about the width and the length, and we'll be able to collapse this down to a function of just the width or just the length. We'll be able to get by with this with a lot of the nature's processes and laws that we look at, and we'll be able to avoid, for the most part, functions of more than one variable. A much more advanced topic that we're going to stay away from by and large. Oh, I'm sorry. What did I do? Go away. Okay, speaking of formulas, let's take our favorite. Distance is equal to velocity times time. Again, I just want to introduce one more piece of vocabulary, if I could. The distance is equal to a function of time, equal to the velocity times the time. T would be the independent variable. D would be the dependent variable, the distance, because I'm making the distance depend upon the time as the velocity times the time. But in the study of uniform motion, right, we're working with a constant speed. V is thought of as arbitrary but fixed. In the discussion, the constant motion, the constant speed doesn't change. So for example, you could have d is equal to 3t or 1/7 of t or minus 2t. Yeah, minus 2t is a very nice distance function. If we're calling distances in the right direction, positive, well, you call distance moving in the left direction negative. It's a perfectly nice function to move in the opposite direction. So these would be all valid uniform functions of distance versus time. Mathematically, of course, these are all different functions. They all have different table of values, for example. But again, thinking in terms of our applied mathematics, if we're looking at uniform motion, then we think of all these v's as a parameter. Okay, they're different, they're arbitrary, but they're fixed for the discussion. So this would be the parameter v, and all these would be the same constant motion function. Another example would be the quadratic function. We look at one quadratic function, ax squared plus bx plus c. There are, of course, an infinite number of those because you can choose a, b, and c to be anything. But when you want to talk about the quadratic function, you would write it down using the parameters a, b, and c. Okay, so just another piece of vocabulary that we'll be using. The parameters of our laws of nature will usually are very, very important constants of nature. So we'll be talking about parameters. Okay. How do we interpret this new notation that we have here of function of values? Suppose a ball is thrown straight up from the top of a cliff, 80 feet high, and we throw it up with a speed of 64 feet per second. Then the height of the ball can be actually given as a function of time. And we will derive this equation in due time. For now, we'll just take my word for it that the equation of the height of the ball depends upon the time. These are all different scenarios. We will study all these scenarios later on in the course. We can drop it straight down. We can throw it straight up. We can throw it out from a cliff. Here, our scenario here is I've kind of combined these two. I want to throw it straight up from the cliff, or we could simply throw it out from the ground. We will look at all of these scenarios and try to derive the function of h as a function of time. But for now, let's just focus on this one. I'm standing up on top of the cliff and I throw it straight up. This would be the function. How do we understand this? How can we begin to read this, turn this into a language? Well, let's have a table of values in front of us. I think that'll help. And so what height did we start with? What was the starting height? I just look at the function. Well, right, that would be when the time is zero. That's what, when the time is zero, what's the height when you start at the time? And of course, we go ahead and compute f of 0, and the two t terms cancel out, and you're left with 80. Yeah, sure enough, the height starts at the top of the cliff. That's where the ball begins. I could ask the question, are there any other times when this ball has a height of 80? No, I don't want to search through and find that, yeah, after 4 seconds, the height is 80. I want to have algebra answer this question, okay? The question I'm asking is, when does f of t equal 80? Well, f of t is 80 plus 64t minus 64t, c squared. Well, when is that equal to 80? What is the t that makes that? That's an algebraic question. It's an algebraic equation to solve. Okay? I can solve this equation. The 80s cancel out. I'm left with 64t minus 16t squared is equal to 0. I can factor out the 16t, and sure enough, I have two solutions. I have when t is 0, which I know, we got that one. It's where the ball starts. And yes, when t is equal to 4, okay, right here. Okay, we don't need to search through the table of values. Algebra can tell us these answers by solving the functional equation. And notice the expression I'm using. This is a functional equation. I'm taking the functional value and setting it equal to a particular value and saying, what is the independent variable for that dependent variable? Algebra, find for me that particular value in the table of values. Another question, when does it hit the ground? Well, what does that mean? When does it hit the ground? When the height is 0. It hits the ground when the height. We're trying to translate these questions into these functional expressions. So it'll hit the ground when the height is 0. So what is the t that makes the height 0? Again, we could search our table of values, but let algebra solve the problem for us. And so we'll set the computational rule equal to 0 and find that solution. I can factor out the 16 and get a very nice quadratic expression. You could factor that, by the way, right there. You can put a t and a minus t on the back. That'll work. But if you're not comfortable with that, you can go ahead and multiply through by a -1. Yeah, -1 won't change anything. All the solutions will stay exactly the same as long as you multiply every single term by a -1. Okay, even the 0 times -1 remains at 0. So we may be more comfortable factoring an expression like this. The factors of 5 will give us that -4. Okay, and sure enough, we have the 5. We have our table of value. We also get t is equal to -1. Does that have any meaning? Well, in terms of the problem, not really, because 1 second before the ball was thrown up, I don't know, I guess it was in the person's hand. So maybe the value should be 80. It was sitting there on the top of the cliff. But could it be interpreted some other way? When we have more tools of analytic geometry, we can go back and answer that, because we know the answer is 80. We know that these are two solutions to the problem. F of 5 is 80 and f of -1 is 80. Could that possibly have any interpretation? We'll see a bit later on. And the last question I want to ask before we'll finish here, we'll stop here for the day. If it hits the ground at t is equal to 5, we've agreed to that. At t is equal to 5, the height is 0. The table, we can continue on with the table and say that f of 6 is -112. At the 6th second, it's at a height of -112. Does that have any meaning? Well, again, that's a yes or a no. It depends upon your physical interpretation, okay? If it hits the ground, no, the f of 6 really should be 0. It's still sitting on the ground, okay? But in fact, if there was a hole in the ground where you dropped it, okay, it would continue going down past the ground, continuing moving down in this hole below the surface. And in fact, this equation would tell us just exactly how low the ball would be after that 1 second below the ground. After the 6th second of its flight, it would in fact be 112 feet below the ground. So yes, this does have meaning if you want to interpret it physically that way. Okay, we will stop here and begin our story of analytic geometry next time. I stopped on time. I feel good about that. So are there any questions about anything that we've talked about here or last time or anything? Can I clarify anything from anybody? And remember, okay, guys, adolescents don't know this, but we do. If you have a question, there are at least 3 other people who have the same question. So I encourage you to, we have a little bit of time if you do, to ask a question if you have any.
I have one.
Yes.
The equation, the 80 plus 64t minus, is it 16t squared?
This guy here.
Yeah. Where did that come from?
Well, we're going to derive that. You have to take that on faith from me right now.
Oh,
We
okay.
we will derive that equation. Matter of fact, we will derive the equation for every single one of these scenarios. Galileo did this for the first time, and we will go through Galileo's argument, one of the most beautiful and one of the most important arguments in the history of physics. For the first time, Galileo takes a natural motion, a motion in nature, and turns it into mathematics. First time anybody was able to do that, and we will follow in his footsteps, and this will be one of the equations that we derive.
Thanks.
Another question.
Peter, this is an algebra question that came from earlier in the PowerPoint.
Yes.
And Andy and I we looked through the PowerPoint, and in
What slide? What slide are we
I
talking
think
about?
it's the third or the fourth slide that you were on from the top, from the very beginning of the PowerPoint.
This
It
guy
might be-
here?
Yeah, it might be that one. It's so small on my screen, I can't really see it. And maybe this is a matter of I need to just go back through and look at.
Is this it here?
I think so.
Well, I'll
And
tell you
maybe
what, I'll tell, if you're not sure, why don't you, check that out and shoot me an email, and I'd love to
Okay.
answer that question for
Yeah,
you.
I'll do that.
So if you're unsure what equation we're talking about, it's not going to be a good question.
Yeah, I made a note of it, but lost track of it.
Please shoot me an email on that.
Will do. Thanks.
Okay. Any other questions before we go? All right, guys. So we will start. Yes, question? Okay, we'll start the story of analytic geometry next time. Okay, have a good week, everyone.
Thank